Ever wonder how cities move water for millions? Or how oil travels thousands of miles through pipelines?
Well, it really all comes down to one fundamental problem: friction, specifically between the fluid and the pipe walls.
See, inside that pipe, a thin layer of fluid actually sticks to the wall, creating drag that just robs the system of energy.
So to figure out exactly how much energy is lost, engineers start with one key equation to find what's called head loss.
Now, most of these terms are pretty straightforward to measure. The real puzzle, though, is finding F, the friction factor. And that F totally depends on how the fluid is flowing. Is it smooth and laminar, or is it chaotic and turbulent? That changes everything.
For simple, smooth flow, F is easy. It just depends on something called the Reynolds number. Think of it as a chaos score. If that chaos score, the Reynolds number, is below 2300, the flow is considered laminar. Nice and simple.
But of course, in the real world, things get messy. For turbulent flows, pipe roughness suddenly becomes a huge factor.
So how do you find F when the flow is turbulent and the pipe is rough? Well, engineers have a master tool for this.
And here it is. This is the Moody diagram, and it is the key to solving this entire complex problem.
Okay, I know it looks a little intimidating, right? But it's really just a map. You just follow the numbers to find your F. All right, so we've cracked energy loss from friction, but that's not the only thing going on inside that pipe.
For that, we need a new tool, the Nusselt number. It tells us how much the fluid's motion is boosting heat transfer.
It's simple, really. A higher Nusselt number just means you have way more active convective heat transfer.
And here's the really cool part. Just like friction, heat transfer is also tied to that same chaos score, the Reynolds number.
Think of them like two sides of the same coin. Friction factor is about momentum loss, while the Nusselt number is about heat transfer.
These dimensionless numbers are like the engineer's secret language. They boil down all that complex physics into a single useful score.
And that's why they are so essential. They're the toolkit for designing everything from car radiators to giant power plants.
These numbers are the keys that unlock the physics of fluids, which makes you wonder what else is just waiting to be decoded.